Yeah, please go ahead.
All right. Thank you very much, Professor Kim, for inviting me here. So I'm going to start with, so this is a very interesting setup. It's like circular, so I'm going to try to walk around. I hope that's okay. I'm going to start with a pretty trivial question because we're on the topic of AI, right? And AI is probably what's very, very trendy now. What do you guys think is AI? How do you guys define artificial intelligence? Zara, maybe?
It's like a compute mechanical process defined by computer that we run as the users to help us conduct certain functions.
Okay, sounds good. Uh, sure.
Yeah, I have another microphone.
Okay.
I suppose, yeah, like lines of code that we as humans determine how to train and teach in certain maybe meaningful manners or algorithms such that hopefully it can help us to identify relationships, predict more numerical trends in ways that like humans can't really calculate at that scale and depth.
Okay, interesting. So how many of you here think that you use AI, or how many of you use AI a lot? So most of you, right? And what AI do you guys use? Chat, Claude, and Gemini. Anything else? Okay. So the reason why I'm saying this is because so artificial intelligence essentially is machine intelligence that has some form of reasoning, some form of perception and learning abilities, right? So we want this computer algorithms to learn in some sense and to be able to reason and give us some useful inference or perception, right? And architecture, so all of you are from architecture school, right? I suppose most of you are from architecture school. Okay, so that's good. So you guys do design, right? I'm from architecture school, but I'm not a traditional designer in the sense. So I'm not like Professor Kim. I don't do design. We work on buildings in very different ways. So architecture essentially is a very spatial thing. And so I'm going to start by asking you guys to think about this, right? So if you think about the common large language models that you guys use, Chat, Claude, Gemini, whatsoever, if you ask Chat or Claude or Gemini a simple question, right? Like you have a you have an image of a building, you have a door, you have a window, and you can just try it out, right? Ask Chat, ask Claude, Gemini to reason where is the window in relation to the door, or um where is the living room in relation to the bedroom. Most of the time, Chat, Claude, or Gemini is going to give you a wrong answer, right? Because LLMs, they don't inherently have spatial reasoning abilities. So in this first test, I'm going to start with this before I do the intro. So in this first test, which is what one of my PhD students is doing, we developed a set of questions, which we call spatial reasoning questions for architecture, uh, pertaining to building performance analysis, right? Solar exposure, daylight, point time and luminance, natural ventilation. And we threw this whole bunch of questions to the state-of-the-art models, including commercial models and your open source models like Quen and things like that. And do you guys want to get what is the average score? Just 100, right? Like maybe Gemini, Claude. So we give them a whole set of architectural building related questions. Do you guys want to guess what's the score on average? Zara? 25%? Okay, it's a little bit better than that. It's between 50 to 60%, right? So that means that for most of the architectural built environments class that we give to these LLMs, most of the time they are doing they are getting a score that's kind of similar to a rough guess, right? So if you hear things like, yeah, AI now is going to, LLMs are not going to bring us to artificial general intelligence or urban spatial intelligence. So if you hear things that, okay, LLMs or AI is going to replace architects, I don't think so. What I think is that AI will make us a lot more productive and efficient and help us do our work better, right? And to the work that my group is some of them over here today. As we know, the world is building a lot of new building stock. Most of the buildings that exist now, they will still continue to exist by year 2050, and the global building floor area is expected to double, right? So think about this. We are adding buildings to the world equivalent to a New York City every month. And in 2017, the United Nations said that to meet our carbon goals, which obviously we know that most of the countries, we can't meet our targets already, so some of the targets are being revised. Every building on the planet must be net zero by 2050. But right now, currently less than 1% of the buildings worldwide are net zero at this moment. So as you know, Singapore, we have the Singapore Green Plan, right? And we have the super low energy SLE building scheme. How many of you, do you guys want to make a guess how many buildings in Singapore are currently SLE? Super low energy.
5%.
5%? Okay, so this lady here says 5%. Do you want to guess how many? 50% are super low energy. Okay, it's way lower than that, right? Even for Singapore, which is we have pretty good regulations, right? We have a pretty good regulatory body. But even so, the numbers are way lower. We have less than 100 buildings that are currently super low energy. You still think about that, right? And so this brings me to the work that my team is doing. We call ourselves CDCD Lab. And of course, some of the faces here, I haven't updated this. We use AI for climate resilient cities in different ways. And so today I'm going to maybe talk about some use cases. And I'll cut across scale, right? So if you think about AI and climate resilient cities architecture, we can actually look at this from different scale. So we'd like to break down our work into three key skills. One would be urban. So urban would be entire cities and entire counties in the US or entire Singapore. So this is mostly an urban skill, right? And then where we go down to designing and running models and simulations for individual buildings, this would be at building scale. And then at the human scale, it's also very interesting, right? So because this affects how us as individuals perceive architecture, perceive thermal comfort, perceive space use, so on and so forth. And so today what I'm going to share is some use cases and work that we have done, cutting across all these skills, and how we can use AI in what we think are meaningful ways to help us solve some of our problems. So of course, we can keep this interactive. If you have any questions, just interrupt me. This is the first time I'm doing this very interesting setup. So we'll start off from the urban scale, right? So cities, as you know, are both a cause of and a solution to climate change. So cities, many cities around the world, right? They are nexus of economic growth. People are moving towards cities because of better opportunities. Some people, they move from rural areas to cities in search of better job opportunities and things like that. And there are a lot of issues underpinning this, right? One is that it's starting to get congested. We are building more density. And in many of the cities, they design what they call climate action plans, right? So I have some examples over here. You have the Boston's climate action plan, you have Chicago, European Union, even in European Union's climate action plan, buildings play a very significant role, right? And then we have Singapore's green plan, so on and so forth. But if you drill into all these green plans, right, and as you know in Singapore, if you start building buildings, this is where our regulatory body will require you to do some submissions, right? And then your buildings will have to be green to a certain extent, PCA green mark, and as well as other schemes, right? So, but if you look into all these plans, right, we work across many cities. During my PhD and now, I think we have worked across almost 20 cities. If you drill into all these green and sustainability plans, right, you realize that sometimes while the targets are quite clear, the pathway to get to the targets are sometimes not so clear, right? So some cities will say that, okay, in by 2050, I want all of my buildings to be green and net zero. And that is a very easy target to say, right? Like it doesn't take much to say that, okay, this is my target. But if you look into the details, a lot of cities actually don't know how to get there. because most of the building stock is already there. And for new buildings, can they really all be net zero? I think this remains to be seen, right? So the first thing that we do is what we call urban building energy modeling. We use artificial intelligence and we merge it with physics-based models. So what's physics-based? What is a physics-based model? Shuya, what do you think is a physics-based model?
It's our results. And the most important is that it's also kind of
Okay. Okay, no, that's a good answer. Physics-based models are based on real-world physics, right? Like how heat transfer between your interior and exterior, the temperature differences. So what some of these conventional models do, how many of you have used Cloud Studio? Most of you. Cloud Studio, probably made use. Okay. So if you use a simulation software like Cloud Studio, Viva for Rhino, Honeybee Lab, underpinning it are physics-based models, right? These are a whole bunch of equations. So we click run or simulate, there's a black pop-up that always come up and you see a whole line of code or text or equations running. So these are physics-based models, right? And what it does is it's solving a whole bunch of thermal and heat balance equations between the interior, exterior, convection, conduction, radiation, and it solved all of this, right? So physics-based models conventionally at urban scale, it takes very, very long to resolve. So think about this, right? If you have one building and you need to solve all the equations on all the heat balance equations, it takes pretty long, right? And the whole city takes even longer. So one way that we do this is through artificial intelligence, of course. We train what we call surrogate models. So we use physics-based models and brute force, and then we run a whole bunch of we get a whole bunch of data, and then we throw them into an AI model, could be a neural network or something else, and then we train it. And this AI model is supposed to give us prediction very, very quickly. Okay, so this essentially is one way that we can use artificial intelligence. And so for this stream of work, what we do is we work with cities, and I'll have examples later, right, that's relevant to Singapore, so you understand how we do this better. But what we do is we work with cities, we look into their existing building stock, what are the current buildings that are in the city right now, what are the new buildings that are going to build, and how we can run this different types of analysis, merging AI and physics-based models to give them scenarios and help them project into the future. Okay, so how many of you have watched, again, a lot of questions today, I have a lot of questions. How many of you have watched Marvel Infinity War? Do you know the one that all of them fought Thanos or something? You watched it, right? Doctor Strange? Anybody watch Doctor Strange? Nobody. Okay, so in Infinity Wars, you remember there was a scene where Doctor Strange did this circular thing, and then he said that, okay, he told Iron Man, right? He told Tony Stark, I projected into 1 million futures. There's only one future that all of you will win Thanos, right? Okay, something like that, right? Something like that. Okay. So essentially what we are doing is also something like that. You think about this. So we are running thousands and tens of thousands of models with physics and with AI and projecting into various scenarios, right? And then we say, okay, this could possibly be a scenario that can help you to get to net zero. Because cities are already there, right? And buildings are already there. So we can't say that, okay, we knocked down some of the buildings, we changed the window to wall ratio, we changed all the glass from single glaze to double glaze. So all of these things, if we were to do abortive work or we change it physically, it takes a lot of time, capital expenditure, and money. So what we do is we say we work with cities. We know that you have a goal. We run tens of thousands of simulations, and we try to do scenario analysis, right? With a fixed amount of budget or resources that you have, what type of outcomes could you possibly get, right? So this is something like what you say, right? Monte Carlo could be different types of simulation methods as well. So in this case, for urban skills, so I work a lot in terms of energy. I call it energy, comfort, health, nexus. So because energy leads to thermal comfort, right? So energy in buildings help us to achieve thermal comfort, which in turn help us to reach our human potential and to achieve some form of health outcomes, right? So in terms of energy, and city scale urban building energy modeling use cases, there are a few that we can look at. One is urban planning and new neighborhood design. I have a use case later on Jurong Lake District. So I think some of you probably know about Jurong Lake District. So that is an urban planning use case, right? Nothing is there. Jurong Lake District is new. Our Prime Minister announced it, I think, last year or the year before. And so the planners want to know what kind of planning parameters that should be, what kind of building design that should be, and what kind of future it could possibly get us to, right? So that's urban planning and new neighborhood design. The second use case is on stock level carbon reduction strategies. So stock level means that building stock that is already there, right? Like for Singapore, most of our buildings are already here. And in many countries, so in Singapore, we operate on a different set of culture and guidelines, right? People don't like to stay in old buildings. So we HDB, I think some of you probably BTO, or some how many Singaporeans here BTO? No? Okay. No, so some of you probably heard about the term, right? BTO, Zara, yeah. So we have the 99-year lease and then maybe 50, 60 years, some of the buildings will be demolished, but in a lot of other countries, buildings stay on for a lot longer, right? They don't have a 99-year thing. It's not like after 50 years, people don't want to stay in old buildings anymore. So we look at building stock and we run these thousands and hundreds of thousands of analysis to see how we can help the existing building stock become more sustainable. So for example, right, if let's say today I'm a government policy maker, I have a limited amount of money, maybe from taxpayers or what I have, let's say 50 million, for example, to retrofit or to improve certain neighborhoods. The question is, where should I put this 50 million, right? So we run this large scale analysis to identify potential interventions that can get us better impact for our buildings, to get us better outcomes. This could mean that we identify specific neighborhoods geographically that we should be improving, or that could also mean that we identify certain types of buildings or certain vintage of buildings that we should be improving, right? So that's for stock level carbon reduction strategies. So stock level is really for policy, for large scale level. We also go down to building level recommendations. For every building is different, right? There's the whole thing about architecture design, everything is unique, and that's the beauty of it as well. So every building is different, every building is unique. We go down to building level as well. And then the last use case is really about buildings to grid integration, right? You think about this right now with the advent and proliferation of EVs, everybody, they're going home, they're going to plug in their EV to the building, or every day morning when you have commercial officers, you go into your office, everybody's going to plug in their EVs to the buildings, and it's going to draw a lot of power. So what's going to happen, right? Can the grid support this kind of load? How the loads are going to shift? We have renewables, right? Solar panels and whatnot, but solar panels only generate energy when there's sun, right? So, and can we actually put batteries on our buildings? Maybe, maybe not. Some homes in the US, they have Tesla power packs as batteries. But in Singapore, because we are resource, we are land constrained, a lot of these issues become more prevalent. So this is something that we do as well. We run these large-scale models to see how we can not only manage the demand and the load, but to balance it as well. Okay, so that's building to grid integration. So this is the very first model that we did for the Boston Redevelopment Authority. So it's called the BRA. It's a little bit different in Singapore. We have Building and Construction Authority and Urban Redevelopment Authority, right? So it's BCA and URA in Singapore. In Boston, it's one body that's doing both these pieces. So the BRA. So this is the very first model that we did, not by me personally, but this was many, many years ago, 7, 8 years ago. And we built what we call a digital energy twin, right, for the entire city of Boston. And so what we use these models for example, to see the demand profile, right? We identify areas where there are energy hotspots, areas where peak energy will be harder to manage. And then you can see the loads over there, right? From the x-axis is the hour of the day. And then you can see when everybody comes in at 8 a.m., energy goes up, right? Residential, public buildings, commercial buildings. And then towards the evening, the peak goes even higher and then it comes down. right? So the question is really, can the grid support some of this? I'm sure you have read news, California, New York, if there's a power outage, the whole city goes down, right? So we do some of this, and then we zoom in to say, okay, can we look at certain specific areas? Can we look at specific areas and see how we can enhance specific clusters of buildings or specific neighborhoods, right? So this is the city, I think it's the Fenway area, and we have identified this as an area that is significant in terms of energy use, and how we can actually maybe use a mixture of renewables and demand type measures to reduce the energy use. And of course, physics-based models sometimes cannot deal with this kind of computational load. I cannot bundle 50 supercomputers together and run it. So what we do is we train AI machine learning algorithms to help us to run some of these things a lot quicker, right? So I won't go into the technicalities of all the models. This is not an AI CS course, but just know that we use AI to speed up this process significantly and also reduce some of the computational workload. So coming closer to home, right? This is a project that I like a lot. It's one of my favorite projects. It's also a project where I'm working with Professor Kim on. Fred Kim is actually with me on this project. So this is the decarbonization model for Jurong Lake District, right? So how many of you have heard of Jurong Lake District? No. Okay. So Jurong Lake District is a new district in Singapore. I showed you some pictures, okay? It's quite an interesting place. So in Singapore, as you can see, we have the Singapore Green Plan. And we know that by 2030, so our ministers went up, right? And we have policy directives saying that by 2030, we are peaking emissions. And then we need to cut, right? We need to cut by 2050. So you look at the curve there, do you think it's that easy to say we suddenly do such a steep cut and it's not, right? Yeah, go ahead.
The previous one, the graph showed that it was ramping based on sort of total energy electricity. And I was wondering, sort of Singapore is not just a city, but a city state. And you have buildings like JTC buildings, which are industrial buildings, which probably consume more energy. And compared to, so maybe on the sort of landscape, you'll see that the heat map will show that it has a lot of energy use. But in terms of the output of like what it's producing compared to, say, HDBs with inefficient aircons, then that I would probably target those inefficient aircons compared to the industries that are actually producing goods and services to like export and things like that. Yeah, so that would be sort of one thing that I noticed, like the proportion of. So it can't be just strictly like how much electricity you're producing, because some of them are like industrial areas.
No, you're right. As in, I completely agree, right? And as part of this project, this is something that we do as well. So we categorize the buildings, all buildings in Singapore into what we call archetypes, representative archetypes. So an archetype could be a HDB building before it's being built with PPVC, after it's being built with PPVC. It could be a grade A office, it could be an industrial building, B1, B2. We break them into archetypes, right? And for every city, this archetype is different. Because this is probably a little bit unique and it's contextually based, right? So we run the analysis and simulations based on archetypes. And then we can have sub-archetypes, right? Depending on how we break it down. And we even have archetypes for NUS. I would share some interesting things about NUS later. But we even have these archetypes for NUS campus itself, right? And then we run the analysis and see which type of buildings or which archetype should we target. So yes, you're right. Maybe in absolute terms, an industrial building or a manufacturing plant might use more energy, but maybe it's worthwhile if you have limited resource to target residential buildings. So essentially, you're right. As in, the concept is basically what we are doing right now, right? So back to JLD. It's an interesting place. It's supposed to be a model for future sustainable net zero district. And it's being anchored by some very interesting setups that we're going to have, right? So we have a new science center, it will have office, play, it will have a new MRT station, and a town hall. And so it's supposed to be a mix, right? It's supposed to be the next CBD for Singapore. Okay, so this is a very nice render that's put up by URA. Of course, none of the buildings exist yet. The question is how we plan for all of this, right? How we make them net zero, and how we make all these buildings and the entire district more sustainable. So this is one project I'm working with Professor Kim, right? Do you guys call him Prof Kim or Fred? Prof Kim. Okay, yeah, so this is certainly one of the projects I'm working on with Prof Kim. He's a co-PI on this. There are a few questions we need to look at this, right? So we have the existing districts that we know already exist, the surrounding area, the greater area of Jurong, right? Jurong already has buildings and HDB, and some of you might live in Jurong. So how can we quantify operational carbon, and how can we quantify energy use carbon in the existing districts? And then how can we use this information that we have to plan for a new district? And that will mean that also we factor in some other important factors, right? Population is expected to change. Our preferences, our lifestyle, the way we commute, the way we use energy is expected to change, right? With COVID-19, for example, what happened with COVID-19? Everybody started working from home, right? So you see office energy use maybe plateauing, and then residential energy use suddenly goes up, right? Because everybody's plugging in their workstation, laptop, your plug load goes significantly higher. And after COVID-19, you realize that things has never been the same again, right? Now people are asking for 3 days working in office, 2 days work from home. All of these have implications. So how can we plan for new districts, and how can we use the models that we have to make this scenario analysis, right? Like your Doctor Strange and Iron Man Tony Stark project into the future. Singapore, we have limited land, limited resource, and how can we design meaningful interventions that will make us more sustainable and resilient? Okay, so as part of this, what we do, very simple. This is academic, so I think I can show this. But this is actually a platform that's being used by URA, our planning agency. It's currently being used by more than 1,000 planners. More than 1,000 planners across agencies, not just in URA. So housing development boards, building and construction authorities, some of them use this planning tool as well. What this does is allow them to draw building massings, right? I think you guys use Rhino or SketchUp, right? So Rhino, SketchUp. So this allows them to draw building massings and plan, right? What is the program? What is the population, the zones, the programming, and things like that. It allows them to do some of this. And so what we are doing here, what Professor Kim, myself, we are going to do here is we will develop the archetypes, as what you mentioned. We will break these archetypes down into individual models, and we will run a physics-based simulation across all these archetypes, and we will train AI models, and then we will host the AI models. So these are some of the archetypes that we came up with, right? So we train the AI models, and we will host it. We'll host these AI models onto ePlanner itself, and then allow the planners to make decisions, right? So every time they change a building or they change a form, as you can see, this is changing, right? Every time they change a building, they change the form, they add sky terrace, they add greenery, they remove certain program, they can see what is the implication in terms of the emissions, the carbon emissions embodied and operational, as well as energy use and things like that. So this will help them make more meaningful and insightful decisions, right? They can compare various scenarios, compare different massings, and then instantaneously they can see the results. Okay, so if I'm going to run a traditional climate studio or Rhino simulation, what's going to happen is that you're going to click run, and then you can go and make tea, make coffee, and then you come back, and your results maybe still have a load, right? So that's one benefit of using machine learning or AI models, is we can split this up very, very quickly. Okay, so I have a lot of slides, so in the interest of time, I won't go into all the details, but this is the core idea of this, right? We have a physics-based model, we sample, we train an AI surrogate, and then we host it on ePlanner, and then that will allow us to run all these things very, very quickly. And as part of this, we also use unsupervised learning methods, and we develop new algorithms, right, that are grounded physics. We call it hybrid physics and AI, because I don't believe in everything you just throw into the AI model and expect it to give a result, right? Because can you trust the result? We know LLMs hallucinate all the time. Can you trust the results? Can you really believe that the results are grounded in building physics? So the answer is I don't fully trust the results. So what we do is we develop this hybrid physics and AI-driven models. And one of them is called, one of the algorithms that we have developed is called a hypercube. So the hypercube concept is very simple. You take a whole building, you imagine the building you take a whole city, you imagine the whole city is like a giant Lego city, right? So I love to play with Lego, right? From young, I always got my mom to buy me Lego blocks. I love playing with Legos. So the thing about Lego is that they have some common denominators, right? You always have the base plate, you have certain sizes, and you have certain shapes and certain colors. So you can think of it this way, right? I can break the whole city down into Lego blocks. I find the common Lego pieces, and then with that common Lego pieces, I can use those common Lego pieces and build thousands of cities. Makes sense, right? The concept. Yeah. So what we're doing here with the hypercube is we are doing unsupervised learning. We're clustering the buildings into based on archetype, based on program use, based on the amount of solar radiation each facade gets, based on the amount of wind, pressure, coefficient, everything that each building gets. We break it down into mini Lego blocks, and with that we can rebuild different cities, right? So here we have applied in San Francisco, Paris, Singapore, and then the results are pretty accurate. Okay, so this is one of the algorithm. I won't go into the details again. This is not a CS class, but the whole concept is really a lot like Lego, right? So sometimes it's on my top line. I keep bring Lego pieces and we play with them, so that's pretty fun. So think about this: we break it down, unsupervised, and then we cluster, and then we use these Lego blocks to rebuild thousands of different cities. So with some of these algorithms and AI method, we also use them to fill up data that we don't have, and use to merge together with publicly available data and then run entire analysis for whole city. So this is actually live. If you have a computer, you can just go to buildings.sg and you can play around with it. This is a live platform. What this does is that it shows the carbon emissions map for the whole of Singapore, both embodied and operational carbon. And we overlay it with the URA master plan. So you can, these colors are actually the different master plan. I think, yeah, so orange, yellow is probably residential. So you can see for each area, how much carbon emissions is being incurred. We can normalize it to get per meter square. And then you can make interventions and make decisions, right? So this is live, you can play with it right now, buildings.sg. And then this is the interface for the embodied carbon. So we also have operational carbon. Okay, so this is just one use case of how we use AI on city scale to reduce energy use, to improve thermal comfort. And now that I'm done with city scale, I know that I have 1 hour, so I try not to bore you guys and keep you guys for lunch. The next part is we're going to neighborhood and building level, right? So from city, I'm going down to neighborhood and building level. So I picked up one project that's probably close to everyone's heart. Where's this place? Do you guys know? Utah, right? Okay, it's very obvious. Okay, so this is Utah, right? So maybe some of you want to make a guess. I think this is recorded, so I probably shouldn't give out the number, but I'm not sure if I should tell you guys the number, but how much do you guys think this NUS, the whole campus, we spend on energy bills so far? Maybe I should not use the mic. Because our president would murder me. How much do you guys think we spend on energy bills? NUS, the whole campus. Anybody want to guess? Okay, Singapore dollars, that is Singapore dollars, right? My home, one I'm paying about $300. The one year I'm paying about, with 12, about 3,006, 3,000, about 4,000, $4,000 just for electricity per year for my house. I live in a 3-bedroom apartment. So NUS, the whole NUS, for example, how much do you guys think we pay energy bills per year? No? Okay, so somebody said 100 million, right? Anybody else want to guess? Okay, so she would guess 5 million, right? Anybody else? That's what I guess. You want to guess? 100 million. Okay, I cannot tell you the exact number. Y'all will up tomorrow, but okay. So what I can say that is very close to the number. Okay, it's pretty close to the number. So think about this, right? Even if we even if we can reduce just 5% of it, how much money are we saving per year? It's a lot, right? It's a huge amount. And just the museum itself, the NUS museum, the black color museum, right? Inside there are 2 dinosaurs. Every month they're paying, I think, more than probably more than 50,000, about $50,000 in energy bills, right? Because they need to keep the place cool and run and keep the exhibits in perfect condition, right?
The irony of using fossil fuels to keep the fossils
Yeah, so think about this, right? Even if you can save a little bit, it's quite a lot already, right? Even if you can cut 1%. So in NUS, we have this project, we call it Cool NUS Beam. So Cool NUS is because we want to cool the whole campus. And this is a strategic project commissioned by the NUS president, right? So he had a lot of foresight. He said that, okay, we are seeing population growth, we might admit more students, and then with climate change, everything, we need to ensure that NUS is a cool campus. And we want to be the sustainable campus for the future, right? So this is a project that's within NUS. We call it Cool NUS BIM. BIM stands for BIM, not building information modeling, not your Revit models or what. So BIM stands for baselining, evaluating, action, and monitoring, right? So we set the baseline, and then we evaluate the baseline, and then based on the baseline, we think of interventions that we can do, and then we monitor these interventions to see whether they are effective or not, right? So there are some radical ideas. Now, actually, we are doing our campus master planning for the next phase. There are some radical ideas that my team is exploring. Of course, not everything will be actually implemented. We are even thinking, can we punch holes in buildings to allow better wind flow? Or can we do away with certain paths so that we reduce the reliance on internal shuttle bus? Can we retrofit certain buildings so that they are more sustainable, right? So of course, SD4 is a net zero building. If you have time, visit Yusof Ishak House, YH. That is also a net zero building, and it uses a lot of natural ventilation, right? Makes more natural ventilation. So we want to be a sustainable campus for the future, and which means that our new buildings when we retrofit certain buildings, we need to take into account a lot of all these considerations, right? It's no longer just, okay, can the space, can the program cater to students' use, cater to the lecture research use, but needs to be in a sustainable way. So for QNUS, we support in various fronts. So the first two are probably the ones that we support the most, right? So we have a target by 2030, we want to cut 15 to 20% EY by 2030, and we want to reduce 30% scope 1 and scope 2 emissions. Okay, and of course, we want to defend against climate change. We know that the entire region of even Singapore will be heating up right in the upcoming years, 2030, 2050, 2080. So how can we defend against this, right? And then we are going to plant, I think the target has gone up, so it's probably 120,000 trees by 2030. So it used to be 100. So what we do for this, I think some of you might not know, but NUS, we actually have the densest network of weather stations on any campus in the world. Okay, you guys probably don't know, right? So if you walk around, right, here's the spot. We can play this game later or something, right? Called spot the weather station game. So if you go around, you can see all these little, not some are bigger, these weather stations around, right? So we have about 40 weather stations at ground and roof level. We have infrared thermal cameras, we have map towers, so these are the locations, right? So we can go around trying to spot all our weather stations, and we actually have the most number of weather stations on any campus in the world. So this gives us fine-grained microclimate as well as environmental data and variables, which allows us to then set the baseline. So with the baseline, we evaluate, and then we come out interventions, and we say, okay, how can we design meaningful interventions, right? So one intervention that we are currently testing in engineering is we apply cool paint. Right, we apply cool paint, and then we measure cool paint, normal paint, what is the energy loads that's being reduced, and then whether cool paint is effective. And then, of course, cool paint has a higher premium cost than normal paint. But we have decided that every new building that is in NUS, and every time we are going to repaint the building, we are going to repaint it with cool paint, right? So that's one intervention. And so the whole, oops, yeah. Yeah, and so the whole idea is that how AI comes in, right? So of course we have some data. We collect microclimate data, but can we project into the future? Can we fill up areas that we don't have data? And that's how we use AI, right? We train different types of models, recurrent neural nets, transformer models. So transformers are not, so you know GPT, right? Generative pre-trained transformers. Transformers are not only used for language models, right? Like transformers can also be used for time series models to predict weather, to predict climate, to predict energy use, and things like that, to predict solar radiation. So we train all of these models, and we use them in different forms, right? Yeah, so this was the archetype question that I think you brought up, right? Different types of buildings in NUS. So we are also looking at this from a archetype perspective. So the different colors are the different types of buildings, right? Some are hostels, some are lecture theaters, uh some are canteens and whatnot. So we also look into this from an archetype perspective, and then we combine this with the microclimate data that we have, and we see, okay, which buildings should we target first? What type of buildings can get us more impact and help us help us reach our targets faster. And another thing that we do, again with AI, is we have these thermal cameras, right? So look at this, we have these thermal cameras that take images of different facades, and we know that facades, they tend to heat up during certain parts of the day. It's not possible for us to, I mean, we don't have that much money to install these thermal cameras on every single building, right? So that doesn't make sense. So what we do is we have a few thermal cameras, we take images on certain buildings, and we train a model. We train an AI model that we can then say, okay, can we use that model to predict these facade images across every single building on campus? And that will help us make good decisions, right? So we are using data from only 2 thermal cameras. We train an AI model that we say, okay, this model can be generalized. And then we use that model to predict facade surface temperature for different buildings all around campus. And then we can target, right? We can see some of the facade at a certain time of the day is heating up a bit more. Right. So this is another way we are using AI. Yeah, so this is less relevant. This is just a course that I'm teaching AI for sustainable design, so I skip this. We also do some of this in education. So this is an NUS digital twin that we have. You can play around with it. It's also live. So one little tip, right? If you go to Rhino buildings, all the Rhino models are free, right? You can download them. Any buildings. So these are all developed by students, right? Students in the class. I cannot claim that they're 100% accurate. There are built models as well. There's a LiDAR scan across the whole campus. So if you want a campus model, the whole campus model, you go to Rhino Urban, you will get high fidelity LiDAR scan geometry of the entire campus, 290 buildings. Yeah, so this is the one, right? You can see it's very detailed. So it's a lot more detailed than OpenStreet Maps. So if you want, you can just download it at nus.com. And so another thing that we do is we say, okay, we do a lot of these things in academia, right? We do a lot of these things in academia, but what is the point if research doesn't get translated to actual use, right? We want industry to use this, we want policymakers to use the research and the tools that we built. And can we then that will give us meaningful impact, right? We're just not just writing papers or sitting in labs and doing research. So what we have done is we take all the algorithms that we have developed, all the different approach, and we put it into a tool, and we spin it off as a startup, right? That we call Urban Flow. So I'm sure you've heard of agentic AI. How many of you have used Figma or Canva? Okay, most of you have used Figma or Canva, right? So think of this as like a Figma Canva for urban and building design. So you know Figma, you have multi-layer mode, right? You can have like Zara and you what's in it? Yeah. So yeah, you can have Zara and Z designing together, right? Or Figma, it's like Google Docs, right? So this platform is essentially like a Figma for building and urban design. But instead of Zara, Z, and human beings, some of these could be AI agents. Meaning you can design with a team of humans together with AI agents, right? And each of the AI models that we have developed, we port them into individual modules, which we call flow modules. So the entire platform is called Urban Flow, right? So we have this mini flow modules: energy flow, carbon flow, cost flow, climate flow, heat flow, light flow, comfort flow. So some of this could be AI agents, right? Like if you're designing with somebody like an architect, designing with your engineer, you can say, okay, now I need to know the energy use. Can I pull up the energy flow agent to run some analysis based on my building geometry and things and give me the results, right? So this is the energy flow example. It's as simple as like talking to chat and or Gemini, right? But instead of having zero spatial intelligence, this is architecturally and urban intelligence driven, right? So you can ask questions, okay, what should be the recommend me window to wall ratios, change the window to wall ratio, what will be the impact on energy use, what will be the impact on carbon, what will be the impact on cost even, right? So this is a agentic platform that we try to merge some of the work from our lab. And then another thing that we are doing is something that's close to my heart, is that in a lot of these cities, throughout a lot of these cities that I work in, Singapore, London, Boston, these are all pretty developed places, right? I would say we are quite well off. Our government agency, URA, is probably the best or one of the best government agencies that I've seen of all the government agencies that I work with. Some cities don't even have a GIS department, right? So not saying that we are doing everything right, but we have pretty much good resources, right? But in the world, more than 1 billion people live in informal settlements. And these places, they sometimes don't even have energy, not to mention thermal comfort, right? And interior temperature can heat up to as much as 45 degrees. So heat stress, heat risk has a lot of issues for human being, right? Sick illnesses, in many cases, even death. So this is a picture that I like to show. Do you remember? Yes, what this guy is doing? Coupling electricity lines, okay? Don't know. You want to guess? Okay, she's actually stealing electricity.
The tool is to take electricity.
Correct. So he's stealing electricity. So in many places in the world, electricity doesn't come as energy or electricity doesn't come as easy, right? Like us, we go home, we switch on our plugs and everything, we get power, right? So this guy is actually stealing electricity. He's pulling his own wiring and then attaching it to the infrastructure to steal electricity and route it to his house. So this is very dangerous, right? You can fall, you can get electrocuted and things like that. So some things that we are using AI for, and we hope that it's meaningful, I think is where we can derive some impact, is to really design interventions and solutions for some of these places, right? Informal settlements. So look at this, right? Will you call this a building? Probably not, right? Yeah, from architectural sense, you probably wouldn't call this a building, right? But more than 1 billion people currently live in places like that, and these places can heat up very significantly. They are not ideal conditions for people to live in, and this is also why we feel like some of the methods and tools that we do can actually enhance sustainability and livable conditions for them, right? So even simple interventions like radiant barrel foils and mylar emergency blankets can cut down the interior heat. So what we are doing now is we fly drones. Yeah. So I think Rohan, one of my team members, is also looking for a helper. So if this is something that is interesting to you, feel free to reach out to me. We can work with that, Rohan. So what we are doing is we customize drones and we make these drones into flying weather stations. So you have a drone, right? We attach like sensors on top of the drones. We run analysis to see how the propellers and the wind speed will not affect the sensors recording. And then we fly these drones. So we're going to fly this first around NUS campus. I think we'll be getting approval soon. And then we hope to bring this to different regions around the world where there are different types of informal settlements and fly our drones. And then with the data that we collect, we train AI models, right? So that we can predict for other regions that we don't have data, because it's not possible for us to have 1 or 2 drones and fly across every part of the world. So we can train models, and these models can always predict other regions or other scenarios. Okay, so I've talked a lot about, I think I have 5 minutes left, so I quickly wrap up. I have talked on some use cases of AI for urban scale and then building scale, and then now I'm going down to human scale, right? So this is also another campus study by Lu Jia, and this was exhibited in the URA's Well-being in a City exhibition. So on a human level, AI can also help us make certain predictions, right? So we know that people perceive heat and comfort very differently. Like for example, my wife is very flexible. So she always say Chinese people. Yeah, so Chinese say that which translates to thick skin. Right? So my wife doesn't say I'm very thick skin because I'm not flexible. So we know that humans perceive comfort, perceive architecture, perceive urban design very, very differently. So in this stream of work, we are thinking, can we use AI models to predict some of these perceptions, right? How people might feel about space, how people might perceive about space, whether they like the space, whether they don't like the space, with all the space that actually built. So traditionally, what urban designers are doing is they do focus groups, by do surveys, by field they are training AI models, right? So we take a scene, and you have seen that in the video, right? You can take a scene, the whole scene, right? You can split that. We can use segmentation models to split that into various parts, right? So one scene, certain parts have certain amount of greenery, certain amount of pavement, certain amount of trees. So these are all images taken on campus, right? So actually, these are all scenes around NUS campus, and we are scaling this to the whole Singapore. But you can see these are all different parts of campus, and what we do is we actually survey students. Okay, never mind, I'll use this. So what we do is actually we build a platform and we survey students. We ask like hundreds of students what they feel about different spaces, whether you like the space, whether you don't like, whether you think it's too hot, whether it's too cold, what do you think we can include to make the space more comfortable, what do you think shouldn't be there, and then we gather all of these survey results, and then we train the AI model to predict perception, right? So which means that then we can do scenario analysis. If new population or new students come in, we can predict what they might like, what they might not like, and we can use these results to engage with architects and urban designers to help us make better decisions. So this is really a human skill. Okay, and here, so this is just the machine learning part of it, how we split each scene into with computer vision into so this one, if you want to play with, you can just one of the models that we tested was a Meta's segment editing model. So if you want, you can just Google Meta segment editing, and you can use that to do a segmentation, right? To see what's the proportion of sky, greenery, buildings, and everything. And then we also tested the colors, the surface materials to see which of the space people like it more, which people like it less, why do they like it, why do they not like it. Okay, I think I have 2 more minutes, so I wrap up, just 2 more slides. And another thing that we do, 2 more things that we do, it's pretty fun, is we train this agents, right? We are using AI models as proxies for human beings. Okay, so I set up certain agents, and I give these agents personas, meaning that, what is your name? Nicholas. So you're male, you're year 4 student, right?
No, actually.
Oh, yeah, staff. Okay. So there are some students. So Dara is a female, obviously, she's a first year PhD student. So I get this whole bunch of AI agents, and then I give them personas. So one persona could be Nicholas, NUS staff, age between 25 to 30, likes to wear t-shirt, likes to wear pants. Another persona could be Zara, which is a year 1 student, has an architecture background, has a very good style, knows how to design buildings, likes to wear t-shirt and things like that. I give these AI agents personas, and I throw them into a simulator and see how they would behave, right? So see how they might use energy, how they might switch on the air condition, how they might move around, and this will help me predict what could happen in various different situations, right? So one last slide is we throw these agents around on campus as well. And I like Lego, right? So I make them into Legos. Okay. Do you guys like this place? This model. Does it look familiar? Sorry? Yes, this is Utah, right? So this is the model below that is Utah, right? So what we are doing is, in this study, we are trying to see if we can improve walkability and thermal comfort in Utah. So we throw all of these agents, and we run this simulation, right? And so every time the agent walks, you can see this little Lego boy. Every time this Lego walk, we can run the analysis for sky exposure, wind speed, wind weather temperature, UTCI, PT, visual comfort, and a composite comfort index, right? So we are simulating how people might feel, how the whole bunch of students might want to walk, the routes that they might take, and the things that they might do across campus. And then we can say, okay, this will give us a more data-driven and empirical feedback approach. If we say, okay, we think that this path on this path, we should. Yeah. So I think I'm at time, but happy to, of course, answer any questions. And yeah, if you are keen to know more, you can always reach out to Professor Kim or myself. And yeah, thank you very much. Brett, over to you, maybe.
Thank you, Chin. I'm gonna let one of my staff, my team member to MC the questions there. But thank you so much for this, all the project. I haven't seen all these projects before, so it's quite fascinating to see what you've been up to. And I have a quick question to start with. A lot of times, like the examples that you show, like shows a lot of way to how a human can navigate all these data with the interface, right? So my question is, as a designer, what is the best way to have a interaction with this interfaces that you guys have developed? What do you uh, how much like this going back and forth will influence our built environment? Because like a lot of times when you do a simulation, you can do many trials and then find the best optimized solutions, but then there's also the design part, right? How do we navigate between these two? Also, especially with this interface that has been developed with the AI.
Yeah, so I think it's a really good question. And that's something that we have been thinking about for some time, right? So for me, I don't think that AI will replace human beings. And if everyone here took classes on generative models or GANs or diffusion models, you will know this term called mode collapse, right? So what mode collapse is essentially because the training data is based on what is already there. So then after a certain point of time, what the models will generate are just kind of repetitive, right? And then there's mode collapse because the models really will lack creativity in some form. So I don't think AI is ever an approach or tool to replace human creativity or architects for all that matter. I think we use it alongside us. So I give you one example, right? For me, sometimes when I'm writing maybe journal papers or conference papers, I think that my title is not good enough. I think I can probably change the title a little bit, make it better. So what I might do is I might ask Gemini or Claude to give me some options, right? And then I will decide, okay, I take a little bit of this, I take a little bit of that, and I put it together, and then I have some of the new ideas, and I come up with a title that I like. I think the same for building design, like as an architect. So one thing that something that we're working is called I think it's form to climate or something, which is quite similar to what Shuwen is doing. So architects at earlier stages, what they do is sketches, right? Or sketch to climate, sorry. What they do is sketches, right? In the conventional manner, architects they sketch out very quickly. So can we use AI models to quickly convert these sketches into performance metrics? So I did simple sketch. I use AI models to convert them very quickly to a CAD, and then convert with a surrogate AI model, convert to performance metrics. How much daylight certain places will get, how much solar radiation, how much energy. So this means that I am short-circuiting the whole process, right? I don't need a draftsman to do the CAD. I don't need a modeler. I don't need a ESG consultant or sustainability consultant to simulate energy use. Architects sketch something, we get performance metric. And then I can say, okay, maybe the model can give me some other options, and then I decide. Right? So I think of AI as a kind of short-circuiting all these things that conventionally we need to do, automating some of this, and maybe helping to iterate in terms of ideas, but not replacing the creativity or the human ingenuity part. Yeah, back to you, Prof. Kim. Or
I have a question.
okay, sure.
Curious how the trade-offs or not trade-offs are being like between your building scale and also urban scale optimization when the performance goals are not aligned. Like what's optimal on the building scale is different from like scale on the urban context. And maybe the second question is since your perception is subjective, so how do you ensure consistency and reliability of these models when human feedback is being used on this training?
Okay. So these are two fantastic questions again. So the first question, right? I don't think it's really about the best model for all use cases. I think it's about the right model for the right case and the right skill. So which means that again, similarly, if we were to extrapolate this to chat, Claude, Gemini, right? It's not one model. Maybe you guys pay one subscription to use that for everything, right? But for me, Claude is very good for coding tasks. Gemini, Nano Banana for nice renders, Chat for general purpose. So back to your skill question, it's the same thing, right? Like I train different models for building level and urban skill. I don't say I train one model and I expect that model to be good for everything else. So that means that the data that goes into the different models, the scale that I'm training it at, the granularity will be different. So a model that supports me on building design will be different than a model that supports me on urban planning decisions, per se. And to your second question, yes, that is true. Humans are fickle, right? And humans are a lot of times illogical and irrational, right? And that is why we usually try to validate our models. So if let's say, for example, think of it as two probability distribution curves, right? If I have a perception model and I were to predict human perception based on your persona, and then if I run it 100 times, and if I survey you, let's say 100 times, so I survey hundreds of you, hundreds of similar personas, 100 times, and then these two distribution curve kind of matches, and then I can say that, okay, the model is somewhat validated, right? Of course, not 100%, but then the model is validated with human perception in some ways. And that model can always be a live and evolving model. I can always update it. And the beauty of this is, so one thing that's very interesting is that the beauty of this is that we did quite in-depth analysis. So we trained these perception models on using AI agents and human surveys, right? And we realized that, okay, both humans are irrational and sometimes illogical, right? But the amount of time and the proportion of irrationality that humans might make is actually quite similar to the amount of times the models might make illogical decisions. So that's actually quite interesting. Think about it, right? That means the models can sometimes also exhibit some type of irrationality. So one example, as humans, sometimes we switch on the air conditioning. The natural thing to do is you close the windows, right? Make sense? But for some reason, maybe 10% of the time, sometimes you just forget, or sometimes you just don't bother, right? You think you want a bit of that natural ventilation, but yet you want to on the air conditioning. You on the air conditioning in the car, but yet you wind down your windscreen. So that I would classify as maybe not a very logical behavior. But sometimes we do that, right? And then when we train the model and we run the model, we realize that the model makes some of these illogical decisions the same proportion of the same amount of time, which means that it's a very interesting finding, right? In the sense the model can actually kind of somewhat be logical most of the time, but be illogical some of the time, and that proportion of illogicality or whatever you call it is actually matching humans' decisions. Yeah, but I think that's interesting. That's something that we need to look into further, right? I don't have all the answers right now. Because humans are the hardest thing to predict, right?
Thank you. Any question from the
I very appreciate your lecture and have get a lot of insights about how to predict like building scale and urban scale, many indicators and simulation results. I'm just very curious about like AI can do a lot of things, like it can predict urban scale data, but sometimes the data in urban is not very sufficient, like maybe the energy use or the building stock data we can not have very efficiently. So how to validate our AI prediction results is align with the real world data. I'm very curious about this, and also maybe the also although we have maybe have a lot of architects about the whole urban scale buildings, but maybe we can not know exactly what the equipment or the layout in it, so that we cannot so that the even in the same architect, the energy use and some other indicators may be very differently. So how can we deal with these uncertainties in research or in practice?
Okay. So again, these are very good questions. I think you're probably a PhD student, right?
Yeah.
Okay, yeah, you are a PhD student. Okay. So these are very good questions. For the first question, it's about data at scale, right? So the easiest way and the way that we trust the most is usually ground truth validation, right? We validate with ground truth data. So one example, and when I did my PhD, I think 4 5 years ago, we didn't have machine learning algorithms, right? We needed to know the window to wall ratio of every building in Boston, right? We don't know the window to wall ratio. And the window to wall ratio, we know affects light gain, which affects energy use. So the easiest way to validate this with ground truth is like hire 2 RAs, right? To go to Google Map and draw it out. Make sense? Yeah, because that way the accuracy will be quite high, right? It won't be super low, as in maybe humans will make mistake, right? But I hire 2 RAs, maybe you and Shu would just spend 3 months just to draw out all the windows using Google Maps, Google Earth. Yeah. And one way that we can validate that is, let's say we train a model, and then we use the model to predict window to wall ratios now. And then I take your RA, human annotated window to wall ratios, and I match it, right? And I see what's the error. So I could say that, okay, with an error of 90%, 80%, something that I'm happy to accept. Because at urban scale, if you're looking at 100,000 buildings, and we plot the distribution curve, some will be less, some will be more, but the errors all even out, right? And this is also a perennial question in artificial intelligence. In building science, 80-90% is something that I can accept, right? But in healthcare, can I accept a model that's 90% accurate? If the model is predicting cancer cells based on images, 90% accurate means 10% of the time the model is giving a wrong diagnosis. So this also applies to different domains, different verticals. In healthcare, I cannot accept 90% or 80% accuracy, right? But for building science, maybe 80-90% in terms of window to wall ratio is something that I can accept. And the best way, of course, is to validate with ground truth. Yeah. So to your next question is
How to deal with the uncertainty?
Okay. Uncertainty. Yeah. So that's a very good question. So one thing that we are developing now for NUS university campus is ENSEMBLE. So we call this an ensemble model. Okay. So do you guys know like random forest, XGBoost? Okay. So the concept of random forest is that you have a lot of trees, right? So what we are doing is we build something called an ensemble model, meaning that for every building, there's definitely some uncertainties, right? Even for campus itself, UCI cannot tell me the parameters for all buildings. They don't know, right? Some they know, some they don't. So you think about it as a bunch. I think all of you use Rhino and Grasshopper, right? All of you use Rhino and Grasshopper. Okay, so think of it as 10 parameters, right? I have 10 sliders. For those that I know, I can fix the value on the sliders. For those that I don't know, I can have a range, right? I can have a range. Let's say the window to wall ratio, I don't know. So it might be between 0.3 to 0.9. But maybe maybe something else like the U value I know. So think of it as 10 sliders. I can fix the value of the sliders that I know. And then for those I don't know, I have a distribution and a range. So it could be a Gaussian distribution, it could be a uniform distribution. But that's not the point, right? So for my ensemble model, instead of running the analysis and simulation once, I run it 1,000 times. And in that 1,000 times, I fix the parameters that I know. And then for those range that I don't know, for the 1,000 models, I will sample within the range. And then for the 1,000 results, I combine them into what I call an ensemble model. So this will mean that the results are no longer one number, but it becomes a range and a distribution. And I think that's a better approach most of the time, because if policymakers ask me, okay, what is the energy reduction 10 years later, if I can give them one number, I will be here, I'll be super rich, right? Because I can predict the future. Right. So I think everything is really about risk management, right? So I can now what this ensemble model does is that I can say that, okay, I'm pretty confident that it will be this number, but there will be a 20% chance that it might exceed, there will be a 20% chance that it might be below. Yeah, so that's one way we can deal with uncertainty. Of course, another way is we can do sensitivity analysis. We can use more advanced Bayesian models and things like that. But that would be one way that we can kind of deal with that. So what we're doing for campus infrastructure is we're going to take this, we're going to port it into a tool for them, and then when they say, okay, what interventions I want to make, then we show, okay, we show a range right within one number. Instead of UI 200, we show, okay, the mean, the median might be 200, but then there's a range, right? You could go above, you could go beyond, and it's more like a statistical perspective to it. Does that answer the question?
Yeah, thank you so much.
Okay. Yeah, Sarah has a last question.
Yeah, please come up with the thank you.
Thank you for the presentation. I think it's very insightful. I have one question following up from the previous discussion that we need to use the right model for the right scale and the right use case. So when you explain, you have like project across like different scale with like a very different context in each model. So what is your process in, like scoping the data and then the process itself when you develop the pipeline for the analysis? Because like you need to know like what is the important things that you need to consider in each scale and each use case. So is there any like general guidelines for the process that you have in your lab?
Got it. Still a good question. I think that's a really good question. I think we should start thinking about these pipelines. We do have kind of like a fixed structure, but sometimes we like to look at it in terms of what are the outcomes that we should promise, right? Like for example, we will start a HDB project to map temperature and other heat maps across the whole Singapore. So then there are other KPIs or outcomes that the policymakers want, right? Like, okay, the accuracy should be within 0.9 degrees Celsius. They need to have a certain, they want a certain resolution, like 3 meter by 3 meter, and they have certain targets. So now we look at outcomes and what are the outputs that we promise or we commit to, and then we work backwards, right? So to get kind of outcomes, what type of data we need. Then if you don't have, then should I buy weather stations? Should I apply my drones? Should I set up a new manpower to get that kind of data? So we look at what are the outcomes that we want, and then we work backwards to see what kind of data that we need. And then with the data that we need, we test various models, right? Because AI models really like a lot of training of these models is sometimes hard science, right? Like we know that okay, certain models might work, but we don't know the hyperparameters. We need to tune them, we need to tweak. So then we always need to iterate and play around. So once we look at outcomes, then we go back, see what kind of data, what kind of models, and then if we are wrong, we go back again to get more data, to retrain the model, and then it's back and forth process. Yeah. So of course, in terms of outcomes, some outcomes are more confident, of course. Some if it's more cutting edge or something that nobody has done before, then it's something that I'm less confident that okay, maybe we can work towards it as a stretch goal, but maybe we should commit to 0.2 degrees Celsius accuracy or 10% of performance, something like that. So I think iterative process.
Thank you. No questions.
Okay, I think we're good.
Thank you, Chen.